Thank you, Maciej. Thank you for giving me this opportunity. I'm sorry I couldn't make it for the rest of the conference. So I will speak on our joint work with Stanislav Apanasenko, and the title is here. So what is Gurevich-Pitaevskii problem? We look at Korteweg-de Vries equation with these coefficients ut plus ux plus uxxx equals 0 with a particular initial condition. U of 0x is cube root of minus x. So it's, I showed it here, right? It's here, right? Cube root of minus x. So it has infinite derivative at the origin, right? So it's a singular initial condition, and it is studied in many papers, and it's known that oscillatory zone appears. So here is the result of numerical, numerical calculation of this solution, and you see, so this is the initial condition, right? Semi-cubic parabola, and you see oscillatory zone appears, and it grows. It becomes thicker. It becomes broader as time increases, right? So more and more oscillations appear. I'm sorry. Yeah, there is another Gurevich-Pitaevskii. So Gurevich-Pitaevskii problem is to construct an asymptotic expansion of this solution, to understand this solution. They did this work numerically, Gurevich and Pitaevskii, long ago. And there is another Gurevich-Pitaevskii problem, namely with a step-like initial condition, which is similar. You can think of infinite derivative here. It's also called a dam break problem. You can think of two layers of fluid separated by a dam. When it's broken, okay, then oscillations start. Actually, in both initial value problems, the behavior is very similar. Oscillatory zone appears. This problem was studied by many different techniques, and there are asymptotic expansions in this region. It's called the leading edge of the, it's called dispersive shock wave. This solution is called dispersive shock wave, or angular bore, right? There are two equivalent terminologies, right? So this is the leading edge of angular bore, and this first peak which appears here is treated in applied maths as a soliton, the leading soliton, right? And then there are other solitons following. Oops, no, what's happening?
Sorry, maybe there's a naive question, but when you say asymptotic, this is in T or
in T. I will write down the expansion, right? Then there is this end of the angular bore is called the trailing edge or harmonic edge, and there is another asymptotic expansion at the left edge. Then there is the main asymptotic expansion is in the middle, and normally this is done using Witham averaging theory. Why it's happening? What you do, you kind of glue in a modulated periodic solution of KdV, expressed in terms of an elliptic function, where parameters, there are three parameters in a periodic one-phase solution of KdV. These parameters are allowed to vary, right? And the system that governs variation of these parameters is called Witham system, Witham averaged equations. So typically, this is how this problem is approached, but there was an alternative approach which avoids Witham averaging theory. It was developed, to the best of my knowledge, by Suleimanov. And this is the approach I will follow, because there is a funny equation, Abel equation, that appears in this approach, which we managed to solve in terms of hypergeometric functions. So I will follow approach that doesn't appeal to the Witham averaging theory, right? And this approach describes this zone of developed oscillations when the zone is sufficiently broad. Okay. So as I said, this approach is due to Suleimanov. So first observation is that if you that asymptotically this solution is described by KdV, to which you attach its non-isospectral symmetry, a symmetry which depends on x and t. This is stationary non-isospectral symmetry of KdV. So these two systems are compatible. And this, by the way, without KdV, this ODE is known under the name of P14, Penlever. It's fourth order equation in Penlever-1 hierarchy, right? So in this equation, T is a parameter, just a parameter. It's an ODE, fourth order ODE. It's a Penlever equation. Still it jumps somehow. Can't understand why. Yeah. Right. And there is a theorem which is due to Grave and Claes that this equation, this Penlever equation, so forget about KdV, just look at this Penlever equation. It possesses a unique solution for a fixed t. It possesses a unique solution that tends to cube root of minus x when x goes to infinity, plus minus infinity. It tends to this semi-cubic parabola at plus minus infinity. But this solution, the bigger is t, the more oscillations this solution has in between, right? Somehow it looks as it looks like this. So a zone of oscillations appears here. Something like this. And the bigger is t, the more oscillations you have. And this solution is non-singular, pole-free on the real line, so it's a regular solution. In fact, KdV is well understood for rapidly decaying initial conditions and for periodic initial conditions. Right? Then you can apply inverse scattering. There is the whole machinery. But for this is a kind of non-standard. These are non-standard growing initial conditions, right? There is no general machinery for such solutions. Right, so it was proved by Suleimanov that this pair, and I forgot to mention that if you just look at this equation on its own, then this solution, which tends to cube root of minus x at infinity, also automatically solves KdV. This can be proved. So you don't need KdV. You just solve this equation with this boundary conditions at plus minus infinity. And this solution of Penlever automatically solves KdV, right? Okay, so it was shown by Suleimanov that the zone of developed oscillations is described by the following asymptotic solution. U of tx is root t times. So you have to introduce z and phi, slow and fast variables, right? Z is slow, z is xt to the minus 3 over 2. So why it's slow, when t increases, z becomes smaller, right? It's a slow variable. Phi is t to the 7 over 4 times some function f of z, and everything will be about this function f of z, right? So this Abel equation, it's on this for this function, plus a phase s of z. So this phase is, okay, it's important, but there are several papers written just about this phase, and it's proved that this phase has to equal pi. So it's just pi, right? I keep it at s of z, but this function is pi, right? So the only unknown function here is this f of z. And this variable is fast because as t increases, t to the 7 over 4 grows, right? So it's a growing variable. Right, so, and these coefficients, V0, V1, V2, so I assume to be 2 pi periodic in the fast variable, in the variable phi, right? So the problem is to calculate these coefficients. it's done in the standard way. You just substitute this ansatz into here and here. You differentiate and equate terms at powers of t, and then you get quite messy equations for v0, v1, v2. For v0, the equation is nonlinear, and for v1, v2, all subsequent terms of the expansion, these equations are linear, but they depend on v0. Right? These equations are solved for v0, and I will show you a solution. And it surprisingly, if you just ignore all these other terms, so this, just this bit is already almost indistinguishable from the numerical solution, right? In the zone of developed oscillations, it's just almost identical. By an eye, you wouldn't distinguish. It is convenient to associate with this function f of z another function which is called r of z, which is exactly this expression, 7 over 4f over fz minus 3 over 2z. Somehow this quantity appears in the calculation. If you substitute this ansatz into here and here, somehow this thing appears, r of z. And it's convenient to work with this function r of z. Furthermore, this function r of z is not arbitrary. It must satisfy this ODE. It's just first order ordinary differential equation, right? With this particular coefficients, all coefficients are uniquely determined. They're actually uniquely determined by the normalizing coefficients here, and then these are also determined by the coefficients of KdV. Right? It turns out that, this equation was derived by Vadim Kudashev. But it wasn't, so the whole thing was left at this, at this stage, right? So there is an asymptotic solution. V0 can be somehow calculated in terms of r of z, and v1, v2 can be reconstructed, but this was not done. And this equation was not solved. So our contribution is that we kind of solved this equation in hypergeometric functions. And I will explain some background how it was done, because it turns out that this ODE, simple ODE, is a reduction, is a symmetry reduction of a third order ODE with SL2R symmetry. And we were looking with Stanislav, we were looking at ODEs with SL2R symmetry, like Chazy equation, for instance, right? It has SL2R symmetry, right? So there is a similar third order ODE with SL2R symmetry, whose symmetry reduction is this first order ODE. And since every third order ODE with SL2R symmetry is linearizable by a universal procedure, I will go through this. This equation is also linearizable. In fact, linearizable can be parameterized by hypergeometric functions. I'll show you the answer first. As I said, this equation was derived by Vadim Kudashev, and Kudashev's result was never published in his lifetime. He died early. This was published first in published form, this ODE. Actually, this is the ODE. I copied it here, right, on the blackboard. This is the ODE. It is convenient. So in this form, it probably doesn't remind anything. But if you invert it, if you write it in terms of dz by dr, not of r of z, but z of r, then you just invert this fraction, right? So you get this over this. And this is second order polynomial in z divided by first order polynomial in z. This is the so-called second kind Abel equation. I will go through Abel equations later, right? This is an Abel equation, there are about 100 of different Abel equations, various in various textbooks, and most of them are solved in parametric form. Their general solution is parameterized by hypergeometric functions. Right, so this is the answer. Now, what is how R So what is the general solution to this equation, R of z? So we introduce this hypergeometric equation, right, for W of S. And this hypergeometric equation has parameters alpha, beta, gamma equal to this 3. Right? So let's take this particular hypergeometric equation. Let W be a solution, generic solution to this hypergeometric equation. Let's introduce R as a function of S and Z as a function of S by these formulas. Then the claim is the R of Z solves this ODE. Right? It's a generic solution to this equation. It's for R of Z, it's not Abel equation. For this, for Z of R, it's Abel equation of the second kind, but it doesn't matter. Right? Also, remarkably, this equation possesses a non-generic solution, so-called singular solution. And this solution is algebraic. It's, oops.
Can I ask?
Yep.
So this is first order equation. So you
First.
have one constant of integration.
Yeah.
Hypergeometric will have 2. Is it that one of
It
the
disappears.
disappears?
By scaling, yeah. Scaling coefficient is irrelevant. Yeah, it disappears. Yeah. So you see this. Look at this relation. Oops. At this relation, right? If you look at it as, if you think of it as R as a function of Z, then okay, you have to solve an algebraic equation. But if you want to solve Z, express Z as a function of R, it's a very simple expression, and you can check it solves this, it satisfies this. So I will show you a phase portrait of this equation, and it's clear what, on this picture it will be clear what this algebraic solution means. Actually, it also has some physical meaning in the context of Gurevich-Pitaevskii problem. Namely, this singular solution, it describes apparently as, this was, it was a conjecture of applied mathematicians who looked at this work. So they said that probably the singular solution describes the leading soliton, the first soliton in the angular ball. I will show you some pictures. Okay, so this is sort of the summary of our results. So our results are these formulas for the general solution to this equation. This is our result. This wasn't known. Okay, now let me move on. This is the plan of my talk. I will start, I will say a few words, general words about Abel equations. Then the general structure of third order linearizable ordinary differential equations with SL2R symmetry. And then it turns out that symmetry reductions of such ODEs, like by two-dimensional subalgebra, the symmetry reductions reduce third order ODE to a first order ODE. And in many cases, these first order ODEs are Abel equations of the first or second kind, right? And then I will show you two examples. One is when we take, for this third order ODE, we take the Chazy equation, and then the example 2 shows how Kudashev equation appears in this context. Right, then I will discuss phase portrait of the Kudashev equation, the structure of its solutions, and then formulas for the first term in the asymptotic expansion. And then in the last slide, I will discuss solitonic limits. So this is based on our paper with Stanislav. Okay, so Abel equations. There are two types of Abel equations. These are Abel equations of the second kind, of the first kind, sorry. These are Abel equations of the first kind. So if you ignore this term, what is written here is just a Riccati equation, right, with quadratic right-hand side. So if you add cubic term, called Abel equation. And there is no general universal procedure to solve Abel equation. But there are hundreds of them known with explicit solutions in various textbooks. And this is an Abel equation of the second kind. The only difference from the first kind is that you have this linear factor in front of the first derivative. But it turns out that these equations are equivalent, these two forms are equivalent, right? And this is a general link. From capital U, you pass to small u using this formula, right? And then this goes into this, right? They're related. So it's important that this class of equations is invariant under these changes of variables on here, right? You can reparameterize x and you can reparameterize u linearly, right? So in other words, you have a freedom of 3 arbitrary functions in the equivalence group of this class of equations, right? Of course, coefficients change, but the type of equation is preserved, right? And by the way, using this group, any equation, say, of the first kind can be reduced to a very simple form. You can kill these two coefficients. You can make them 0, and you can make this F3 equal to 1. So every first kind Abel equation can be brought to the form u prime equals u cubed plus some function of x. But at the expense that this function of x can become very ugly, right? So it's easier to keep Abel equation in this form, right? With whatever coefficients they are.
The second equation contains 6 functions, so seemingly they have like more freedom.
You see, but they're equivalent by this transformation, by this change of variables. This can be brought to this form by, it's not of this type. You see, it's 1 over u. It's not linear in u, right? Maybe you can calculate equivalence group, bigger equivalence group for the equation, for the second kind Abel equation. So most of the equations, Abel equations known in the literature are solvable in parametric form via hypergeometric functions. And in Maple, there is even a program specifically written for Abel equations. There is a kind of procedure where you can identify your Abel equation with the ones the ones that are known. Right? So there is a special Maple program that does it. Right? Okay. So now third order. So as I said, Abel equations typically arise as symmetry reductions of third order ODEs with SL2R symmetry by 2-dimensional symmetric subalgebras, right? And then this reduces order by 2. And third order ODEs, so just third order ODEs, general, this is a general third order ODE with this kind of symmetry, so alpha, beta, gamma, delta belong to SL2R. Z transforms in a linear fractional way, the independent variable, and G, the dependent variable G of Z, it transforms in this way. This is a standard transformation formula for the so-called quasi-modular forms, right? For instance, Chazy equation is a quasi-modular form. For modular forms, this would be, instead of 2, you would have k here, and there would be no term, no linear term here, right? So if you put here k instead of 2, then this is how modular forms of weight k transform, right? So modular forms of weight 2 transform like that without this term, and then quasi-modular form, they have this extra bit. In particular, Eisenstein series E2 is a quasi-modular form. Right? Okay, so I'm looking at third-order differential equations with this symmetry. And there is a general construction for them. There is a general formula for such ODEs. So let's introduce 2 differential invariants. A second-order differential invariant I2 and the third-order differential invariant I3. Okay? Both of these expressions are invariant under these transformations. Therefore, any third order differential equation with this symmetry can be represented in the form of a certain of some relation. F of I2, I3 equals 0 relation among this invariants. Or you can say I3 is a function of I2, but it's more convenient to use this because this function I3 can be a very complicated algebraic function of I2. So it's more convenient to write these equations in this kind of unresolved form, implicit form, right? Since equation has this symmetry, it can be linearized by universal procedure. There is a universal way to linearize all such ODEs, just due to the existence of this symmetry. And the procedure is as follows. The statement is, there exists a second order linear differential equation, linear ODE, with some coefficients P and Q that can be efficiently reconstructed, right? Such that oops, I'm on another. So there is a second order linear differential equation with some coefficients P of S and Q of S. S is auxiliary variable, right? With coefficients P and Q that can be reconstructed in terms of this original third order ODE. So let W tilde and W be two linearly independent solutions to this equation, right? Then let's write down the following parametric formula. Z is the ratio W tilde over W, and G is this explicit expression in terms of W, and this capital W is the Vronsky of the solutions, right? It turns out that if you take for any third order equation of this kind with this symmetry, there exists a second order linear equation, right, such that the general solution to this ODE can be written in this parametric form. Yeah? By the way, when you vary how to get SL2R freedom, when you vary W tilde and W as the basis of solutions of this linear equation, you get precisely this SL2R symmetry, right? Once you know this, you can explicitly reconstruct this P and Q, right? Let me skip this step. It's straightforward. You can reconstruct them. So now I will look at a particular case of third order equations where this relation between I2 and I3 is just a linear relation, right? Just a linear relation among I2 and I3, because this will be sufficient for our purposes, right? So I'm looking at relations I3 plus a constant times I2 plus another constant equals 0. These constants are important, right? They are arbitrary, and for different values of constants, you get different interesting Abel equations, right? So this is explicitly how this ODE looks, right? C1 and C2 appear as coefficients here. It's just a linear combination of the invariants I showed on the previous slide.
So those invariants under SL2R, that's what
invariants are under this particular action. We have this particular action of SL2R, right? So these are invariant. Huh?
Is there a Schwarzian sitting in nice form?
Not quite.
Okay.
It's related to Schwarzian.
Yeah.
It's related, but I can't make a precise statement now. Yeah.
Schwarzian appears if you don't change G, if you do fractional linear algebra, but G is fixed.
I see. So this is you think of I3 as a generalized function.
This is the basis of all such invariants up to that order.
Yeah, that's the basis of invariance. One second order, one third order, right? And all the rest, yeah, and there is also invariant differentiation you can generate further. Yeah.
Relative invariance.
These are general invariants. Probably there are. I don't know. I can't say. Right. So let's look at this particular class of equations which depend linearly on two constants, C1, C2. In this case, now I'm doing a symmetry reduction by a two-dimensional subalgebra of SL2, namely translations and scalings. This means that I'm introducing omega and psi by this formula in terms of G. Omega is G squared over G prime, psi is this thing, right? These are invariants of a two-dimensional subalgebra of SL2, right? It turns out that then under this, for these two variables, this third order equation reduces to this Abel equation of the first kind. Right? You see psi omega, psi as a function of omega satisfies this first order ODE, d psi by d omega. So you see here, this is the coefficient at psi cubed, this is the coefficient at psi squared, and this coefficient at psi, and there is no free term. Right? So the right-hand side is a cubic expression in psi. All right? So, and these constants C1, C2, they enter this equation. C2 is here, C1 is here, and so on. Right? So this equation goes to this Abel equation, depending on two constants. And it's the general parametric solution. In this case, for this particular class of equations, where I2 and I3 depend linearly, are related linearly, this linear equation, to which everything can be reduced, right? It can be chosen to be hypergeometric. And parameters alpha, beta, gamma of the hypergeometric equation are expressed in terms of the C1, C2. So the linearizing equation is hypergeometric in this case. And it turns out that if you use parametric representation, this parametric representation from the previous slide, right? And put it into here, right? Use parametric representation, substitute it into here. Then you get the following parametric representation for the Abel equation. So psi is this expression, and omega is this expression. Everything is expressed in terms of, and W is a single generic solution of some linear equation, which is in this case is hypergeometric. So let me go show you two examples. So this is the Chazy equation, well-known Chazy equation, right? Very simple. And the generic solution to this equation is the Eisenstein series E2 of Z. It's a quasi-modular form on SL2Z. So in this case, the procedure from the previous slide gives the following Abel equation of the first kind. Yeah. By the way, this 24, right? Then you get Chazy. So then the corresponding Abel equation is this one, right? And it's and the corresponding linearizing equation is hypergeometric with one of the following choices of const parameters alpha, beta, gamma. They're actually equivalent. It doesn't matter really. You can choose any triple. Right? And then so this equation possesses. Let me go back. So this equation, this Abel equation, possesses generic solution given by this formula, where W solves hypergeometric equation with this parameter. All right? And also this Abel equation possesses an algebraic solution, which is given by this formula. Omega is a function of S, psi is a function of S. This is an algebraic solution. So like singular algebraic solution. All solutions are transcendental. They're expressible via hypergeometric functions, but this special solution is algebraic. This is the case for many Abel equations. So now our case, which gives Kudashev equation. So in this case, for some reason, we have to take these constants. C1, C2, as shown here. Then you get quite a long, messy third-order equation with a SL2 asymmetry, right? The corresponding Abel equation of the first kind is this, right? Is this. And it possesses the following parametric solution: psi as a function of S and omega as a function of S, where W solves hypergeometric equation with one of these choices of constants alpha, beta, gamma. For instance, we can choose this, then we get the following parametric formulas. So W of S solves hypergeometric equation with this alpha, beta, gamma. Okay, this is not yet Kudashev equation, but it turns out that there is a link between this Abel equation and this equation, right? And then if you combine, I'll show you this link on the next slide. So formulas, unfortunately, are quite messy, right? They're not elementary, not easy to memorize. Okay, this equation is related to this equation, right, by a change of variables, which I will show now. And if you combine this change of variables with this parametric representation, you'll get parametric representation for the Kudashev equation, for this equation from the introduction. Yeah. So this is the link. So this R and Z from this equation are related to psi, and omega by these quite tricky formulas, but this is what they are. And furthermore, Abel equation from the previous slide possesses this algebraic solution. If you combine, okay, this change of variables with this parameterization, you get algebraic solution for this equation that I showed at the beginning, right? Okay, now phase portrait of the Kudashev equation. So here, this axis is R, and this axis is Z. So R of Z. And what this arrows show here is the slope, dr by dz. So this curve, purple curve, is precisely the algebraic solution. This algebraic solution of this equation, right? Of this equation. So it has. By the way, this equation has 6 singular points. Singular points are where both numerator and denominator vanish, right? So there are, if you intersect this equals to 0 with this equals to 0, you get 6 points. And they are shown here in blue. 2 of them are singular points of this algebraic solution, and 2 more are here, right? They can be explicitly computed. Their coordinates are known, right? So all this, so you see all these solutions. For instance, there is a solution going from this singular point to this singular point. If you follow these arrows, you can see how they foliate the plane. And but all these solutions that you obtain following black arrows are hypergeometric. They are transcendental. They are not algebraic anymore. And remarkably, for this to solve Gurevich-Pitaevskii problem, you need a special solution of the special hypergeometric solution of the Kudashev equation, not a generic one, not algebraic one, but a special one. Namely, you can see here there are 2 singular points, and there is a solution which connects them, which kind of asymptotically tends to the singular points. So you need precisely this solution to make all these expansion coefficients. Remember, there was B0 of Z phi, B1 of Z phi, and so on. All these expansion coefficients. They must be to pi periodic in the first variable phi. So to make them 2 pi periodic, you have to choose a specific, this special asymptotic solution. It's still representable in hypergeometric functions. Although it's special, it's not algebraic. You may ask, so what solution of the hypergeometric equation you take to get this particular solution? There are so-called Frobenius solutions for hypergeometric equation with special monodromy. So you have to take this special transcendental solution of hypergeometric equation. So it's quite subtle, right? Generic solution will not give you 2 pi periodicity. But when you take this particular solution, everything matches perfectly. All right. Now, the last, I have three slides left. Unfortunately, the rest is quite messy, and formulas for this V0 of Z phi, although they're explicit, they're quite long, right? But you can perfectly program them and calculate with them, right? And they work. So I need to calculate this V0 of Z phi from this asymptotic expansion, right? Phi, this is slow variable, Z is slow variable, phi is fast variable, and as I said, S of Z is equal to pi, and F of Z is related to this. So F of Z and R of Z are related by this formula, right? Okay. If you plug this into this pair of equations, for V as a function of phi, you get this formula. You see, V phi squared equals a cubic polynomial in V, right? It's the same equation as for the Weierstrass elliptic function. But it's more convenient to deal with Jacobi elliptic functions in this context to keep track of real validness of the solution. Right, so V can be thought in this form, where R is the same R as here, and A, B, Q is Fz, and A, B, C, and K, the modulus of the Jacobi elliptic function, are to be found. So when you substitute this ansatz into here, you can find all this A, B, C, and K in terms of R, in terms of this R. So everything is actually determined by this R of Z. All right. And for this function V0 to be periodic in phi, you have to take a special separatrix solution to this. Right. All right, so these are formulas how you calculate coefficients A, B. So A and B are given by these formulas, and C and K are expressible in terms of R from these two formulas. Right? In particular, you see, for this function to be 2 pi periodic in phi, this B over Q has to equal complete elliptic integral over pi, because this is kind of period of Jacobi function. So, and it turns out that this identity, it's quite non-trivial to prove it, by the way. This identity holds only for a special separatrix solution of this, right? Not for generic solution. All right, so I don't want to load you with further formulas. There are explicit formulas for all the coefficients, and you can calculate with them. So, and I think, this is the picture for the developing angular bore, for the developing or dispersive shock wave. You see, so this the number of oscillations grows, and there are two colors here, like brown, red, and green, and they correspond. So let me go back to the phase portrait. They correspond to this red and green parts of the solution, right? They correspond to respectively left and right part of the dispersive shock wave. All right, and then the last formula, I'll show you. What happens if for of z we take algebraic solution of the Kudashev equation? So R is this, Z is this, sigma is a parameter. So in this case, the modulus k squared is equal to 1. And in this limit, it's the solitonic limit. In this limit, dn squared goes to sec squared, to trigonometric sec function. So solitonic profile. So this ansatz goes to this ansatz, right? And this is a single soliton. And all these parameters can be explicitly calculated. And so you get, okay, I'm not responsible for this statement, but this was explained to me by applied mathematicians working with Andy Loughborough. They said that this is very likely to describe the leading soliton, the first soliton in the developing Andy Loughborough, right? Yeah, okay, maybe I'll stop here.
Questions?
I was a bit lost at the beginning. You showed that to solve with this equation, you need to have two solutions for hypergeometric equations, right? And then you take ratio.
Yes.
But then for particular case of Chazier.
Yeah, when you do this symmetry symmetry reduction by two-dimensional subalgebra, this W tilde disappears somehow. Only W stays. It just disappears from the formulas.
But you still need it?
No, I don't need it. I don't need it. I just need one generic solution. Second disappears.
So in the Abel equation, you had a bit with U cubed.
Yes.
If you didn't have this U cubed, that would be Ricci.
Ricci, yes, that's true.
There is a substitution which turns that to a linear Schrödinger equation.
That's right.
If you were to try the same substitution, will you? Is it the same mass?
No, it won't work. It won't work. Abel equations are not solvable in elementary way in any kind of. And even there is no statement that all Abel equations can be solved in parametric, can be linearized in parametric form to some kind of hypergeometric equations. No, there is no general statement like this. There is no way to solve a generic Abel equation, as far as I know.
This Abel equation is related to elliptic functions, right? But is there a kind of explanation when this tells which Abel equations are linearizable and some arithmetic behind this?
No, I can't answer. I don't know. But in textbooks, you'll find hundreds of Abel equations explicitly linearizable to various hypergeometric equations. Probably I didn't study this deeply, this theory. Maybe there is some understanding, but I can't comment on this.
Okay. Again.
Mm-hmm.
We will reconvene in 40 minutes. First thing. Remember,
Yeah, there is. Yeah, there is. This guy helped me, but then he left. But he helped me to set. He will help me. yeah?
Yes, yeah.
She'll help you.
Met him at the chronogram. Told him that might be in the afternoon.
Okay. Yeah.
This is my favorite Abel equation of the second kind, which I've never been able to solve. So if you plug it into Maple, will that tell you something? This is a dangerous.
It's 2 now, is it?